A couple of weeks ago, we were talking about the Cauchy integral formula, which is basically a cheat code to compute integrals. And today, we are going to talk about the steroid version of this, which is the residue theorem. It is the crown jewel of complex analysis. Let's see how it works. So, to understand the theorem, we first need to know what is a residue. If a function has singularity, specifically a pole when this function blows up, we can expand it into a Laurent series around that point z0. This is like a Taylor series but also includes negative powers. And out of these infinite sum terms, both right and left, there is only one term that matters, the coefficient of 1 over z minus z0, which we are going to call a minus 1. This single number is called the residue of the function at that point, and it's mathematically the most important coefficient of all this Taylor series. But why this coefficient is so magical, so important? Well, because of the residue theorem. It states that if you want to integrate a function around a closed loop, the answer would be simply 2 pi I times the sum of the residue of the function inside the loop. For example, if we want to integrate e to the z over z on a closed loop around the origin, then the residue at z0 is just going to be e to the 0 going to be equal to 1. You multiply by 2 pi I and you get 2 pi I. It's all connected. This also shows that the residue theorem is basically the Cauchy integral formulas on steroids, because it's just more powerful and it implies the Cauchy formula. Now, what happens if we have a singularity outside of the contour? Well, nothing, we can just ignore them. Indeed, the only singularity that matters are the one inside. The one outside, they don't matter at all. We can totally forget about them. You just sum the residue of the poles inside the contour, you multiply by 2 pi I, and that's your result. This doesn't sound great though, because we basically move the problem of computing integral to the problem of computing Laurent expansion, which is not exactly optimal because they are kind of gross. But fortunately, there is a shortcut to find these residues. But before we jump to the formulas, we need to refresh a little bit what a pole is. A pole is a specific type of singularity where the function blows up to infinity. The order of the pole is simply the highest power in the denominator that causes blows up. For example, if you have 1 over z minus 1, it's going to be a simple pole of order 1 at z equal to 1. And if you have 1 over z minus 1 to the power 3, well, that's a pole of order 3 at the point z equal to 1. To compute residue of function at poles, we do the following. If we have a simple pole, which means a pole of order 1, then we consider the function f of z times z minus z0, and then we take the limit at z goes to z0, and that's our residue. If the singularity instead is of higher order, so it's a pole of order n, so square, cubed of any other power, then we take the n minus 1 derivative of the function multiplied by z minus z0 to the power n, and then we evaluate this limit as z goes to z0, and divide by n minus 1 factorial. Let's put this into practice. So let's try to compute the integral of e to the z over z squared plus 1 over the circle of radius 2. As always, we start by identifying the singularity of this function. And in this case, the only singularities are when the denominator is equal to 0, which means that z can be equal to plus or minus I. So we draw our complex plane, and then we put the two singularities at I and negative I. Great. And then we are integrating on the circle of radius 2, which means that it's gonna enclose both singularity, and whenever we write it like this, we always understand that we're integrating counterclockwise. Great. Now the two singularities are in, and next step is to factor the denominator. So what we do here, we are integrating over mod z equal to 2 of e to the z over, and now we use the rule of the difference of product. In this case, we get z minus I times z plus I dz. And this tells us that we have a pole of order 1 at I and a pole of order 1 at negative I. So we can use the residue theorem to compute this integral. Is going to be equal to 2 pi I times the residue of the function at I, so e to the z over z minus I times z plus I, plus the residue at negative I of e to the z over z minus I times z plus I. Okay? And as I said before, the two are going to be two poles of order 1 because the denominator vanishes linearly there, and that's the reason why it's of order 1. Great. So now, how do you compute this residue? So since they are pole of order 1, there is a really easy way of doing it. So we have the residue at I, so we are going to cover the pole at I, and then we just plug into I in whatever remains. This means that the first one is going to be equal to 2 pi I times e to the I divided by 2I, plus, and what we do here, the same thing, so we cover the pole at negative I, and we plug into negative I in everything else. So we get e to the negative I over negative 2I. And we can simplify this a little bit as 2 pi I times the hyperbolic sign of I, and the 2I actually simplifies. So at the end of the day, the result is pi times the hyperbolic sign of I. And that's it. As a second exercise, let's try to compute the integral of z squared over 1 minus z whole square on the circle of radius 2. So as before, let's identify the singularity. The singularity is when the denominator is equal to 0, so in this case z equal to 1. So as before, let's draw our complex plane. Z equal to 1 is here, and then we are integrating over the circle of radius 2, so this is 2, and this is our lovely circle, and we are always integrating counterclockwise. Okay, great. So there is only one singularity inside, and in this case I can immediately read it off that this is a pole of order 2. Why? Because the denominator goes to 0 at z equal to 1, and I have a square here. Okay, this tells us that using the residue theorem, this integral is going to be equal to 2 pi I times the residue at z equal to 1 of the function z squared over 1 minus z squared. Okay, and now how do I compute this residue? Well, in this case, it's a pole of order 2, so I have to use the general formula. So I know that the residue at 1 of this function z squared over 1 minus z all squared is equal to the limit as z goes to 1 of 1 over the order of the pole minus 1 factorial. So the order of the pole is 2 minus 1 factorial, which is going to be 1 factorial, which is just 1, times the derivative respect to z, taken the pole minus 1 amount, so in this case the pole is of order 2, so just the first derivative of the function, so z squared over 1 minus z squared times z minus 1 squared. Okay, this means that in this case it's going to be equal to what? Well, z minus 1 and z minus 1 simplifies because I have a square, so this 2 goes away. And now the first derivative of z squared is going to be just z, and when I take the limit to z, and when I take the limit at z goes to 1, I'm going to get 1 over 1 factorial, which is 1, times 2 times z evaluated at 1, which is 1, so this is just 2. This tells us that this integral is equal to 4 pi I. And that's it. This is your result. And now, one of my favorite tricks on all mathematics. Let's say I want to compute the integral from negative infinity to plus infinity of 1 over x squared plus 1, and we don't want to use any trig substitution to do it. There is no complex number here, but we can force it into the complex plane, replacing x by z and integrating over a giant semicircle in the upper half plane. Let's look at this contour closely. It consists of two parts, a flat segment between minus r and r, and a curved arc making a semicircle in the upper half plane. Our function, 1 over z squared plus 1, has a pole at I and negative I. But we notice that only the pole at I matters for this integral actually. Why? Because there is only a pole at z equal to I, the other one is outside. So we can compute the integral over this contour by residue, and that's when the magic happens. Let's start by computing this integral by residue. So as we were doing before, it's going to be equal to 2 pi I times the residue at I of the function, 1 over 1 plus z squared, and this is going to be equal to 2 pi I times the residue of this function at I is going to be equal to 2i, 1 over 2i. This goes away, so this is equal to pi. Great, so this is your integral through residues. Now, this integral over omega r, which is all this arc, how we can compute it also. So, is composed of two parts. One is the integral between negative r and r of 1 over 1 plus z squared dz plus the integral over the circle CR of 1 over 1 plus z squared dz. Now, let's notice something. That if we consider the limit as r goes to plus infinity of the integral between negative r and r, 1 over 1 plus z squared dz, this one is going to be equal to the integral between negative infinity and plus infinity of 1 over 1 plus z squared dz. And this one is exactly the integral we were starting from. Okay, see, this one was the integral we wanted to compute from the very beginning. You can substitute x and z, it's just label, so it doesn't really matter. So great. So all these equalities is telling us that pi is equal to this integral that we know that as r goes to infinity converge to the one that we want, plus this other piece of information. Now, usually what's happening here is that we use a little trick. So pi on this side of the equality doesn't depend on r, but these two instead, they do depend. So let's compute the limit on both sides. What I mean by that, I mean that I want to compute the limit as r goes to plus infinity of the integral between negative r and r of 1 over 1 plus z squared dz plus the integral over CR of 1 over 1 plus z squared dz. And this one I know from the residue calculation is going to be equal to the limit as r goes to plus infinity of pi. Okay, and this one is basically rewriting all this chain of equality. Okay, great. Now the right hand side doesn't depend on r, so I can take the limit. This is going to converge to what we want, so the only one that is left to understand is the behavior of this integral as r goes to plus infinity. So how does this read? This is going to read basically as the integral between negative infinity and plus infinity of 1 over 1 plus z squared dz plus the limit as r goes to plus infinity of the integral over CR of 1 over 1 plus z squared dz equal to pi. Okay, so now if we are able to compute this limit, basically we can relate our integral that we want to compute to something known. Okay, so we will compute the integral basically. Now, how do we compute the integral over CR? So typically what's going to happen is that this integral we can estimate it and it's going to go to 0. And how do we prove that? Well, First things first, let's compute the integral over CR of 1 over 1 plus z squared dz. Now we can parameterize our contour, so now z is going to be equal to r times e to the I theta, and theta is going to go between 0 and pi. And why I say that? Well, because CR, by definition, is this semicircle here, okay? How you parameterize the semicircle is half of a circle, so you use the radius times the angle, theta, okay? And now this angle is going to go from 0 up to pi. That's why I can do this parameterization. Therefore, this integral becomes the integral between 0 and pi of I r e to the I theta, d theta, and this is the differential, over 1 plus r squared e the 2I theta. Okay, this is great. And now the next step usually is to estimate the absolute value of all these integrals. Okay, so let me plug into the absolute value here. So everything stays the same. And now what do? We estimate this is going to be less than equal then the integral between 0 and pi. I bring the absolute value inside, so it's going to be r d theta divided by 1 plus r squared e the 2I theta modulus d theta. Okay, and now this one is going to be less than equal than the integral between 0 and pi of r divided by, I can factor on r squared, so it's going to be r squared times the modulus of 1 over r plus e the 2 over r squared, sorry, 1 of the 2I theta d theta. Now, since we are interested when r gets larger and larger, this term is going to go to 0. So the modulus is going to converge to the modulus of e to 2I theta, which is exactly going to be 1. So this integral, basically, we can say that is going to behave like a constant times r over r squared. Okay? Why is that? Because again, r and r, they stay there. This one converges to 0 as r grows, and this one is going to converge to modulus 1. I'm integrating between 0 and pi, so this constant should be actually pi, actually. We can explicitly compute it as pi. So this one behaves as pi over r. So now, what this chain of equality proves? It proves that if we take the limit as r goes to plus infinity, so we want to take the limit as r goes to plus infinity of this integral here, this means that is less than all of these, and the right hand side though goes to 0 as r goes to plus infinity. This implies that our starting integral over CR of 1 over 1 plus z squared dz is going to go to 0 as r goes to plus infinity. Great, so let's go back to our first equality that we prove. So we have all the chain of equality, and we just proved that this guy is going to go to 0, so I can get rid of it. But this implies that the integral between negative infinity, let's write it down here, the integral between negative infinity and plus infinity, or 1 over 1 plus z squared dz is equal to pi. So we were able to compute our real integral starting from complex number. So a quick graphic recap of what we did. So we considered this contour, which consists of this gamma r, which is this segment between negative r and r, and this circle CR that encloses the pole at I. Then we are taking the limit as r goes to plus infinity. In this way, the contour gamma r will converge to negative infinity to plus infinity, and CR becomes a ginormous circle. After that, we prove that the integral over CR will go to 0, so the integral over this contour is negligible, and at the end of the day, we proved that our starting integral was equal to the residue of the function at I, which was only pi. The residue theorem is our ultimate weapon to compute integrals, and it shows the singularity at just point where the math breaks. They are the DNA of the function, and they hold all the information that we need to study them. If you enjoyed this video, please like and subscribe. Ciao ciao!